Welcome to Still Science Lab. Tonight, we are stepping into the most high-stakes kitchen in the known universe, where the master chefs at the European Organization for Nuclear Research are experimenting with a recipe that hasn't been served since the first microsecond of the Big Bang. We are here to confront a headline that oscillates between a groundbreaking scientific triumph and the ultimate doomsday scenario. CERN just created strange matter, the liquid that can devour Earth. To grasp the sheer existential weight of this development, we must first dismantle our comforting, everyday illusion of permanence. We move through our lives assuming that the ground beneath our feet, the iron in our blood, and the oxygen in our lungs are absolute, final states of matter. We believe that the universe, in its billions of years of evolution, has already found its most stable form. But what if we are wrong? What if the atoms that make up our bodies, our cities, and our entire solar system are merely a temporary, unstable phase of existence, a cosmic mistake waiting to be corrected? Imagine, for a moment, a concept born in the mid-20th century by the visionary author Kurt Vonnegut, a substance called Ice-9. In his fiction, Ice-9 was a unique form of water that was solid at room temperature. It was a seed of absolute stability. The moment a single crystal of Ice-9 touched a body of water, it would force all the surrounding water molecules to instantly rearrange themselves into its own rigid, frozen structure. A single drop in the ocean would trigger a global chain reaction, turning the entire planet into a lifeless, frozen ball of ice in an afternoon. For decades, this was relegated to the realm of imaginative science fiction, a cautionary tale about the dangers of human interference with the laws of nature. However, deep within the subterranean tunnels of the Large Hadron Collider, theoretical physicists are beginning to suspect that Ice-9 isn't just a literary metaphor. It might have a real-world, subatomic counterpart known as strange matter, and it might be the most contagious and dangerous substance in the cosmos. This brings us to the Strangelet Hypothesis, a theoretical nightmare that keeps the world's brightest minds awake at night. To understand a strangelet, we have to look at the Quark-Gluon Plasma currently being brewed at CERN. Most matter in our world is built from just two types of quarks, the up and the down. They are the reliable, boring building blocks of every proton and neutron in the universe. But there is a third, heavier, and far more exotic relative, the strange quark. Normally, strange quarks are incredibly unstable, vanishing in the blink of an eye. But theoretical models suggest that if you pack enough of them together under the crushing, unimaginable pressures found in the hearts of dead stars, they might become strange matter, the ultimate, most stable form of matter in existence. In physics, everything wants to be at its lowest possible energy state. Think of a ball sitting on the side of a steep hill. That ball represents the matter we are made of. It is stable for now, but it is holding on to potential energy. At the bottom of that hill lies the true ground state, a position of absolute, perfect stability. If strange matter is indeed that bottom of the hill state, then our entire world is sitting on a precarious ledge. A strangelet is a microscopic droplet of this ultimate matter, and it acts like a subatomic predator. If a single, stable strangelet were to be unleashed and touch regular matter, the regular atoms wouldn't just bounce off. Instead, they would drop into that lower, more stable energy state. They would be infected. The regular protons and neutrons would dissolve, their internal quarks rearranging themselves to become part of the strangelet. This is the grey goo scenario on a subatomic scale. It is a catastrophic, unstoppable chain reaction. As the strangelet consumes the atoms around it, it grows larger, which in turn allows it to consume even more matter at an accelerating rate. If a stable strangelet were to reach the core of our planet, it wouldn't act like a bomb that explodes outward. It would act like a cosmic sinkhole that pulls everything inward. In a matter of seconds or minutes, the entire Earth, our mountains, our oceans, our atmosphere, and every living soul would be processed through this subatomic meat grinder. Our planet would shrink from its massive diameter down to a hot, dense sphere of strange liquid, no larger than a soccer stadium, yet still possessing the entire mass of the original Earth. We would become a strangelet ourselves, drifting through the void as a silent, indestructible speck of exotic matter. The reason this has moved from a theoretical ghost story to a front-page mystery is the ongoing work at CERN's ALICE experiment. While the world was captivated by the discovery of the Higgs Boson, a specialized team of scientists was focusing on a different goal. They weren't just smashing single protons, they were accelerating heavy lead nuclei to nearly the speed of light and slamming them together. The resulting Quark-Gluon Plasma is the hottest liquid ever created by humanity, reaching temperatures trillions of degrees Celsius, hundreds of thousands of times hotter than the center of the sun. It is a perfect liquid with almost zero friction, a primordial soup that hasn't existed since the literal microsecond after the Big Bang. This is the only place on Earth where strange quarks are produced in massive, chaotic quantities. CERN is essentially building a cauldron where the ice nine of the cosmos could, theoretically, be born. So, the promise of our investigation tonight is as profound as it is terrifying. By pushing the boundaries of what matter can be, are the scientists at CERN playing with a forbidden cosmic fire? Are we building a machine that could accidentally trigger the final correction of the universe, turning our world into a drop of grey goo? Or have we finally stumbled upon the secret recipe of the stars? The Strangelet Hypothesis suggests that strange matter might not just be a doomsday particle, but the very substance that makes up the cause of the most mysterious objects in the sky, neutron stars. If we can understand this liquid, we can understand how the universe truly functions at its most extreme limits. We might be on the verge of discovering a material so dense and indestructible that it could revolutionize armor, energy storage, and aerospace engineering beyond our wildest dreams. We are standing at the threshold of a scientific revolution that forces us to ask if the price of absolute knowledge is worth the risk of absolute destruction. We have moved past the era of simply observing the universe. We are now attempting to cook with its most volatile and contagious ingredients. Tonight, we are going to dive deep into the cauldron of the ALICE experiment to see if we have truly created a strange new reality. Are we the masters of the subatomic realm, or are we just children playing with a match in a room full of gunpowder? The answer lies in the perfect, shimmering liquid currently vibrating deep beneath the Earth. It is time to look into the dark and see if the universe is hiding a true ground state that doesn't include us. To understand why the creation of a strange liquid at CERN is so profoundly unsettling, we must first appreciate the staggering simplicity of the normal world we inhabit. We live in a reality of complex machinery and intricate biology, a world defined by the hardened steel of armored tanks, the sleek titanium of supersonic fighter jets, and the delicate, firing neurons of the human brain. To our senses, these objects are the final word in reality. They are solid, dependable, and seemingly permanent. We have built entire civilizations, fought massive wars, and mapped the distant stars based on the assumption that the stuff we are made of is the gold standard of existence. However, when we peel back the layers of these macroscopic objects, we find that the diversity of our world is a magnificent illusion. Whether it is the high-tech composite armor of a modern main battle tank, or the carbon-based cells of a human heart, everything in the visible universe is constructed from a shockingly limited, standard recipe. At the most basic level taught in schools, we are told that the universe is a giant Lego set made of atoms. At the center of every atom lies a tiny, incredibly dense nucleus, surrounded by a cloud of electrons. For most of the 20th century, we believed that this was the end of the line. We thought the protons and neutrons that make up that nucleus were the fundamental, indivisible marbles of creation. We treated them as solid, impenetrable spheres that dictated the rules of chemistry and physics. But as our particle accelerators grew more powerful, we realized that protons and neutrons aren't solid at all. In reality, they are more like subatomic bags or containers, held together by the most powerful force in the known universe. Inside these bags, the true ingredients of reality are constantly swirling, vibrating, and interacting. These ingredients are the quarks, and in our normal world, the entire cosmic cookbook is restricted to just 2 flavors. This is the standard recipe of normal matter. To build a universe that supports stars, planets, and life, you only need the up quark and the down quark. Every proton in existence is essentially a bag containing 2 up quarks and 1 down quark. Every neutron is a bag containing 2 down quarks and 1 up quark. That is the fundamental math of your entire existence. If you change that ratio, or if you swap one of those ingredients, the bag breaks, and the laws of physics as you know them cease to function. This up and down duo is the reason the floor doesn't give way beneath you, and why a jet engine doesn't spontaneously dissolve into light as it breaks the sound barrier. It is a stable, reliable, and incredibly predictable system. The reason we call this normal matter is that it exists in a state of permanent equilibrium. The up and down quarks are the lightest of all quark varieties. In the cold, low-energy environment of our modern universe, they have no reason to change. They are like rocks at the bottom of a shallow valley. They have nowhere lower to fall. This stability is the silent architect of everything you have ever seen or touched. It allows for the formation of the periodic table of elements, which in turn allows for the complex chemistry of fuels, explosives, and biological life. When a military engineer designs the hull of a submarine to withstand the crushing pressures of the deep ocean, they are ultimately relying on the fact that the up and down quarks inside the submarine's steel atoms will remain perfectly locked in their 3 quark bags. They are betting the lives of the crew on the inventor's permanence of the standard recipe. But there is a hidden tension within these subatomic bags. The quarks inside are not sitting still. They are bound by the strong nuclear force, a force so intense that it accounts for nearly all the mass in your body. If you try to pull a quark out of its bag, the force acts like a cosmic rubber band. The harder you pull, the stronger it snaps back. This is known as color confinement. It is the universe's way of ensuring that quarks never wander off alone. This confinement is what keeps our world normal. It ensures that up and down quarks stay neatly packed into the protons and neutrons that make up our atoms. As long as the quarks stay in their bags, the world remains solid, predictable, and safe. We have spent billions of years in this state of standard reality, never suspecting that the recipe we are made of might not be the most stable version of matter possible. The true genius of the standard recipe is its indifference to scale. The same two quarks that make up the hydrogen in a distant nebula also make up the microchips in your smartphone and the high-grade aluminum of a stealth drone. It is a universal language of construction. We have become masters of this language, learning how to rearrange these atomic bags to create ever more powerful technologies. We have learned how to split the bags apart in nuclear fission to level cities, and we are currently trying to learn how to fuse them together to power our world with the energy of the stars. But in all our technological triumphs, we have never stepped outside the boundaries of the up and down quarks. We have been playing in a very small, very safe sandbox, assuming that the rest of the beach is made of the same stuff. To think about normal matter is to think about a world of strict boundaries. We are defined by the spaces between things, the gaps between atoms, the distance between the nucleus and the electron. These gaps are what allow matter to be soft or hard, liquid or solid. But inside the proton and neutron bags, there is no empty space. It is a dense, high-pressure environment where the strong force reigns supreme. In our normal world, these bags are like indestructible armored vaults. They protect the quarks from the outside world and protect the outside world from the raw, chaotic power of the quarks. We live in the quiet, peaceful suburbs of the cosmos, where the energy levels are low enough that the vaults never break. However, the scientists at CERN are no longer satisfied with the peace and quiet of the suburbs. By smashing heavy ions together at nearly the speed of light, they are intentionally detonating the vaults. They are melting the bags and creating a state of matter so hot and so dense that the up and down quarks are finally set free. In that moment of extreme violence, the standard recipe is discarded. The normal world evaporates, and for a fleeting microsecond, the laboratory becomes a window into the primordial chaos of the Big Bang. But as they melt the old recipe, they are discovering that the universe has other ingredients in its pantry, darker, heavier, and far more mysterious flavors that do not belong in our world. The existence of the up and down quarks is the only reason we have a history, a present, and a future. They are the silent, microscopic soldiers holding the line against the total collapse of reality. But the standard model tells us that there are 4 other types of quarks out there, hidden in the high-energy shadows. In our everyday lives, these other quarks are irrelevant. They are too heavy and too unstable to exist in the cold world of tanks and trees. But what if, under the right conditions, one of those heavy shadow quarks could find a way to become stable? What if there is a third flavor that, once introduced to the recipe, changes the rules of the game forever? If the up and down quarks are the bricks of our world, we are about to discover that the universe might be hiding a form of liquid concrete that can turn those bricks back into slurry. The standard recipe is the only thing standing between us and the absolute, strange reality of the cosmos. We have spent our entire existence as a species assuming that our normal matter is the final destination of evolution. We have built our physics, our philosophy, and our weapons on the permanence of the proton bag. But as we peer into the heart of the Alice experiment, we are forced to face a chilling possibility that our normal world is just a temporary, fragile bubble of stability in a universe that prefers something much, much stranger. We are about to meet the ingredient that doesn't just change the recipe, it devours the chef. The universe, in its deceptive simplicity, hides a gallery of ghosts that were never meant to walk the earth. While our world is built on the sturdy, reliable backs of up and down quarks, we are forced to acknowledge that the subatomic pantry is far more stocked than our textbooks usually admit. Beyond the light, airy ingredients that form our tanks, our telescopes, and our very cells, there exists a heavier, darker, and infinitely more mysterious entity known as the strange quark. This is the third flavor, a particle that behaves so erratically that when it was first observed in the mid-20th century, physicists had no choice but to label its behavior as strange. It wasn't just a clever name, it was a desperate admission that we had found something that didn't fit the elegant, symmetrical rules of the reality we thought we understood. The strange quark is the massive, unruly cousin of the up and down quarks that construct our existence. In the hierarchy of mass, it is a heavyweight. If the up and down quarks are the light, agile building blocks of a standard infantry rifle, the strange quark is the dense, armor-piercing shell of a monolithic railgun. Because of this immense mass, the strange quark is inherently illegal in the low-energy environment of our everyday lives. It is a particle of the extreme, a relic of the high-energy chaos that defined the birth of the cosmos. In the cold, quiet suburbs of the universe where we reside, the laws of thermodynamics are brutally efficient. Anything that is unnecessarily heavy and unstable is instantly discarded. Under normal circumstances, a strange quark is a fleeting apparition. It is born in high-energy cosmic ray impacts or in the hearts of our particle accelerators, but it possesses a lifespan so short it defies human comprehension. In a fraction of a billionth of a second, the weak nuclear force, the cosmic janitor, reaches in and forces the strange quark to decay, breaking it down into its lighter, more acceptable up and down relatives. This instability is the only reason our world is not a swirling vortex of exotic matter. Because strange quarks decay so rapidly, they never have the chance to congregate. They are like sparks flying off a grinding wheel. They are bright and intense, but they vanish before they can set the workshop on fire. For decades, this was the comforting status quo of particle physics. We believed that the third flavor was a temporary glitch, a momentary excitement in the quantum field that had no hope of ever becoming a permanent part of our world. But as we began to peer into the hearts of the most extreme objects in the galaxy, a terrifying conflict began to emerge. We realized that the rules of stability are not fixed. They are entirely dependent on the environment. Just as a piece of soft, black charcoal can be compressed into a transparent, indestructible diamond under the crushing weight of the Earth's crust, the behavior of quarks can be fundamentally altered by the pressure of the environment surrounding them. The conflict at the heart of the Strangelet Hypothesis is one of energy and space. Inside a standard proton or neutron, the up and down quarks are crammed together, vibrating with the intensity of 1,000 suns. But there is a limit to how many quarks you can pack into a given space before they start to push back against each other. This is the Pauli exclusion principle, a law of quantum mechanics that dictates that no two identical particles can occupy the exact same state at the same time. In our normal matter, this principle creates a high-energy crowding effect. The up and down quarks are essentially elbowing each other for room, and this internal tension is part of what gives matter its mass and energy. This is the standard state of being, but it is not necessarily the best state. Theoretical physics suggests that if you take this matter and subject it to the crushing, monumental pressures found in the center of a neutron star, pressures so high that an entire mountain is compressed into the size of a marble, the crowding of the up and down quarks becomes unbearable. At this point, The universe looks for an escape valve. It looks for a way to lower the energy and relieve the pressure. This is where the strange quark, the massive pariah of our world, becomes the hero of the story. Because the strange quark is a different flavor, it does not have to follow the same occupancy rules as the up and down quarks. It is like opening a third lane on a two-lane highway that is paralyzed by a massive traffic jam. By converting some of the up and down quarks into strange quarks, the bag of matter can pack more mass into less space with less internal tension. This creates a hypothetical state of existence known as strange matter, a perfect, liquid-like mixture of roughly equal parts up, down, and strange quarks. In the cold vacuum of our laboratories, this mixture should be impossible. But under the weight of an entire star, the math suggests that this three-flavor mixture is actually lower in energy than the two-flavor matter we are made of. It is more stable. It is the true ground state of the universe. This is the ultimate subatomic betrayal. It implies that our normal matter is merely a high-energy, temporary phase of existence, and that the strange matter is the real, permanent version that the universe actually prefers. The horror of this realization lies in the permanence of the transition. Usually, when a particle is heavy, it wants to decay into something lighter. But in the dense liquid state of strange matter, the rules are reversed. The strange quarks are locked in place by the collective stability of the group. They no longer want to decay. They have found a new home, a more comfortable state of being, and they have no intention of going back to being up and down quarks. It is a one-way door. If you pack thousands of these quarks together under extreme pressure, you don't just get a temporary curiosity, you get a permanent, indestructible strangelet. This is a microscopic drop of the most stable substance in the cosmos, a particle that has finally found the bottom of the energy hill. In our world, the strange quark is a fleeting stranger, a ghost that appears and vanishes before it can do any damage. But inside the Alice experiment at CERN, we are creating the very conditions where these ghosts can become permanent residents. We are smashing lead ions together to create a heat and pressure so intense that the bags of our normal protons and neutrons melt away. In that boiling, primordial soup, the strange quarks are being produced in numbers we have never seen on Earth. We are providing them with the environment they need to find each other, to congregate, and to potentially form that first, fatal drop of strange matter. We are essentially building a bridge to a state of existence that doesn't want to coexist with ours. The conflict of the strange quark is the conflict of the universe itself, the struggle between the normal world we built our lives upon and the strange world that the laws of physics might actually prefer. If the strange quark is the heavier, more unstable cousin in our world, it is the king of the extreme world. It is the core of the indestructible armor of a neutron star, a substance that can survive the death of galaxies. But for a species made of inferior, less stable up and down quarks, the sudden appearance of a permanent strange quark is not a scientific curiosity. It is a biological and existential threat. We are made of a recipe that is only stable because it is isolated from the better version. The moment that isolation is broken, the moment the strange quark becomes permanent, the normal world is no longer required. The universe is a vast, cold machine that always seeks the path of least resistance and lowest energy. If strange matter is that path, then we are nothing more than a temporary obstruction that is about to be cleared away. We have spent our history assuming that being normal was an absolute shield. We believed that the instability of the strange quark was our protection, a cosmic safety catch that prevented the universe from dissolving into exotic slurry. But as we push the Large Hadron Collider to its absolute limits, we are realizing that we might be the ones who are removing that safety catch. We are creating the pressure, we are providing the energy, and we are summoning the third flavor into our reality in massive, concentrated doses. The conflict is no longer theoretical. It is a physical, vibrating reality deep beneath the Earth, where the ghosts of the strange quarks are being offered a chance to stop decaying and start existing. And if they take that chance, if they find the stability they have been seeking since the Big Bang, they won't just be our guests, they will be our replacements. The strange quark is the ultimate bad boy of the subatomic world, and we are currently inviting it into our home, unaware that it has the power to burn the house down just by standing still. This heavy, unstable cousin is the hidden variable that could render everything we know obsolete. It is the dark potential hiding inside every lead-ion collision at CERN. While we celebrate the precision of our engineering and the depth of our equations, we must acknowledge that we are dealing with an ingredient that doesn't play by our rules. The strange quark is a reminder that the universe is under no obligation to remain normal for our convenience. It is a heavy, brooding presence that suggests our reality is just a thin, fragile crust over an ocean of something much darker and much more permanent. We are poking at that crust, trying to see what's underneath, and the third flavor is waiting there, ready to prove that in the grand cosmic scheme, being normal is the strangest thing of all. The transition from decay to permanence is the tipping point of the cosmos. If we cross that line, if we create a strangelet that doesn't vanish, we will have finally found the forbidden fruit of the subatomic pantry. And like every forbidden fruit in history, once you taste it, you can never go back to the world you knew before. The strange quark is the ingredient that could turn our solid world into a liquid nightmare, and we are currently stirring the pot at trillions of degrees, waiting to see if the recipe finally takes hold. The conflict is set, the ingredients are in the cauldron, and the third flavor is ready to claim its place as the final, absolute state of matter. To understand the true terror of the Strangelet Hypothesis, one must first look at the universe as a series of valleys and peaks on a vast landscape of energy. Everything in existence, from the armor plating on a tank to the intricate circuitry of a satellite, is constantly trying to find its way to the lowest possible valley. In physics, we call this the ground state. It is the position of ultimate rest, the place where no more energy can be released and no further change is required. For the entirety of human history, we have operated under the comfortable assumption that our world made of protons and neutrons, or specifically, up and down quarks, is already sitting at the bottom of that valley. We believed we were the final, finished product of the cosmic recipe. But the Strangelet Hypothesis suggests that we are actually standing on a high, precarious plateau, and right beneath us lies a much deeper, much darker valley that we have never seen. This deeper valley is the home of strange matter, and it is a state of existence that does not merely want to coexist with ours, it wants to replace it. The theory describes strange matter not as a collection of individual particles, but as a perfect, seamless, and incredibly stable liquid. In our normal world, quarks are strictly confined inside their bags, the protons and neutrons that make up the nucleus of an atom. They are like prisoners in tiny, separate cells, forced to interact only through the walls. But when you introduce the third flavor, the strange quark, into the mix under extreme conditions, the walls of those cells simply dissolve. In this state, the up, down, and strange quarks no longer belong to specific protons or neutrons. They flow together in a unified subatomic sea. This is a quark-gluon plasma that has achieved a state of permanent equilibrium. Because the strange quark provides an extra lane for the quarks to occupy without violating the laws of quantum crowding, this liquid is denser, more compact, and significantly lower in energy than any matter we have ever touched. It is the true ground state. It is the real bottom of the hill. This realization transforms a strangelet, a microscopic droplet of this liquid, into the most dangerous predator in the known universe. In biological terms, we would call it a contagion. In computer science, we might call it a self-replicating virus. But in the cold, mathematical reality of particle physics, it is a subatomic infection that targets the very fabric of reality. The danger lies in the fact that because strange matter is more stable than our normal matter, everything it touches wants to drop into that lower energy state. Nature is lazy. It always chooses the path of least resistance. If an atom of normal matter comes into contact with a strangelet, it is presented with a choice. It can stay in its current, high-energy, unstable state as a proton or neutron, or it can dissolve and become part of the strangelet, releasing a burst of energy in the process. The laws of thermodynamics dictate that the atom will always choose the latter. This is the central horror of the infection. It is not a chemical reaction or a nuclear explosion in the traditional sense. It is a fundamental rearrangement of the subatomic architecture. If a single, stable strangelet were to escape the magnetic traps of a laboratory and fall toward the center of the Earth, it would not simply sit there. It would act as a seed. Every nucleus it touched would instantly succumb to the infection. A carbon atom in the crust, an iron atom in the core, it wouldn't matter what the element was. The strangelet would strip away the electron shells and pull the protons and neutrons into its liquid embrace. As each nucleus dissolved, it would release energy, heating the surrounding area and fueling the reaction. The strangelet would grow. As it grew, its surface area would increase, allowing it to consume even more matter. This is an exponential, runaway process that ignores every defense we have ever built. You cannot stop it with lead shielding, you cannot blast it with explosives, and you cannot neutralize it with chemicals. You are trying to fight a change in the laws of physics with tools made of the very matter that is being consumed. Imagine the speed and scale of such a disaster. This is the grey goo scenario, but instead of microscopic robots, it is the fundamental building blocks of the universe doing the work. As the strangelet consumes the Earth's core, the planet would begin to structurally fail from the inside out. The immense gravitational pressure that normally holds our world together would suddenly have nothing but ultra-dense, strange liquid to act upon. To the outside observer, the Earth would not explode, it would implode. It would begin to shrink, its mass remaining the same but its volume collapsing at a terrifying rate. The crust would buckle and melt, the oceans would boil away into space, and the atmosphere would be sucked into the growing, shimmering ball of exotic matter at the center. In a duration that some theorists estimate to be as short as a few hours or even minutes, the entire Earth, every mountain, every city, every forest would be processed through this subatomic meat grinder. What was once a vibrant blue planet teeming with life would be reduced to a hot, glowing sphere of strange liquid no larger than a few hundred meters across. A dead, silent, and indestructible relic, possessing the entire weight of our world but none of its history. The frightening aspect of this hypothesis is that it is not a fringe theory or a piece of wild speculation. It is a legitimate mathematical possibility within the standard model of physics. We know that up, down, and strange quarks exist. We know that they can form a liquid state under extreme heat and pressure. The only thing we do not know for certain is whether that liquid is stable at room temperature and low pressure. If it is, then the universe is essentially a minefield. We are living in a false vacuum of stability, protected only by the fact that the infection has not yet reached our corner of the galaxy. We are like a house made of dry wood that has never seen a spark. We feel safe because we have never burned, but the potential for fire is written into the very chemistry of the walls. This turns the high-energy experiments at facilities like CERN into a gamble of cosmic proportions. By smashing heavy ions together, we are intentionally creating the sparks. We are providing the heat and the density required to forge the first drop of this liquid. The hope of the scientific community is that these strangelets are metastable, that they are only stable for a fraction of a second before they evaporate or decay back into normal matter. If they are metastable, they are harmless curiosities, a window into the early universe. But if they cross the threshold into true stability, they become the Ice Nine of the cosmos. We would have created a predator that cannot be killed and a fire that cannot be extinguished. The Strangelet Hypothesis forces us to reconsider our place in the universe. It suggests that we are not the masters of matter, but merely the current occupants of a temporary state of being. We have built our civilizations on a foundation of sand, unaware that a solid rock of strange matter exists just beneath us. If the infection were to start, there would be no warning and no cure. It is the ultimate out-of-context problem, a threat so fundamental that our biology and our technology have no vocabulary to describe it. We are poking at the foundation of reality with the most powerful machines ever built, hoping that the deeper valley we find is empty. But if we find the strange liquid, and if it is as stable as the math suggests, then the discovery of the true nature of the universe will be the last thing we ever do. We are gambling with the recipe of the stars, unaware that the most stable form of matter might be one that has no room for us. The fame of the Large Hadron Collider is almost entirely anchored in the hunt for the Higgs Boson, the elusive God particle that gives mass to everything in the universe. We envision the machine as a vast, subterranean microscope designed to pick apart the tiniest ripples in the quantum field. But while detectors like ATLAS and CMS are focused on the surgical, high-precision task of isolating individual fundamental particles, there is another facility tucked away at point 2 of the 27-kilometer ring that operates on a completely different philosophy of violence. This is the ALICE experiment, a large ion collider experiment. If the rest of CERN is a high-tech laboratory for subatomic surgery, ALICE is an industrial-scale blast furnace. It is not looking for the individual bricks of the universe. It is trying to melt the entire building down into its original, primordial slurry. ALICE is the ultimate cauldron of the modern world, a place where the standard rules of matter are intentionally suspended to recreate the absolute genesis of space and time. To understand the unique mission of ALICE, one must first look at its choice of ammunition. For most of the year, the LHC circulates beams of protons, tiny, single-point particles. These proton-proton collisions are like firing two high-velocity needles at each other. The debris is clean, allowing physicists to spot rare, fleeting events with incredible clarity. But ALICE is designed for heavy ion runs. For a few weeks every year, the scientists swap out the protons for lead nuclei. A lead nucleus is a massive, lumbering behemoth of the subatomic world, packed with 82 protons and 126 neutrons. When two beams of these heavy, highly charged lead ions are accelerated to 99.99% the speed of light and slammed into each other, the result is not a surgical strike. It is a catastrophic, high-energy car crash involving hundreds of individual nucleons. The scale of the energy released in these collisions is so vast that it creates a localized environment of heat and pressure that is fundamentally alien to our modern universe. The goal of this subterranean violence is to create a state of matter known as the Quark-Gluon Plasma, or QGP. As we have explored, in our normal world, quarks are never allowed to be alone. They are perpetually trapped inside their bags, the protons and neutrons, bound by the unbreakable rubber bands of the strong nuclear force. But when the ALICE experiment smashes lead ions together, the temperature at the point of impact reaches a staggering 5 trillion degrees Celsius. This is not just a high number, it is a temperature hundreds of thousands of times hotter than the core of the Sunday. It is, quite literally, the hottest liquid ever produced in human history. At this temperature, the bags do not just leak, they melt entirely. The individual protons and neutrons dissolve into a searing microscopic fireball, where the quarks and the gluons, the particles that normally act as the glue, are finally liberated from their confinement. For a fleeting, infinitesimal fraction of a second, the ALICE detector becomes a window into the absolute beginning of everything. This quark-gluon plasma is the literal soup that the entire universe was made of during the first microsecond after the Big Bang. Before there were stars, before there were atoms, and before there were even stable protons, the entire cosmos was a single, expanding ocean of this searing, perfect liquid. By recreating this soup in a controlled laboratory setting, the ALICE team is essentially performing a forensic reconstruction of the birth of the universe. They are watching how the first droplets of normal matter condensed out of the primordial chaos. It is a scientific endeavor of unparalleled philosophical and physical weight, an attempt to hold the original fire of creation in a magnetic bottle and study its properties before it cools and vanishes. The detector itself is a masterpiece of engineering, standing 16 meters tall and weighing 10,000 tons. It is designed to be the ultimate thermometer and high-speed camera for this primordial fireball. Because the quark-gluon plasma is so hot and so short-lived, we cannot see it directly. Instead, ALICE must track the thousands of particles that come screaming out of the collision point as the plasma cools and freezes back into normal matter. By meticulously mapping the trajectories, energies, and identities of this subatomic shrapnel, physicists can work backward to calculate the properties of the liquid that created them. What they have discovered is nothing short of revolutionary. They found that the quark-gluon plasma does not behave like a gas, as was originally predicted. Instead, it behaves like a perfect liquid, a substance with almost zero viscosity, flowing with a level of smoothness that is theoretically impossible for any other fluid in the universe. However, it is within this perfect liquid that the true danger of the Strangelet Hypothesis begins to take shape. The quark-gluon plasma is a state of total, unbridled freedom for the subatomic world. In this boiling cauldron, the boundaries between different types of quarks are blurred by the sheer intensity of the energy. This is the only environment on Earth where the heavy, unstable, strange quarks are produced not just occasionally, but in massive, teeming quantities. In the chaos of the QGP, the up, down, and strange quarks are all swirling together in a dense, highly pressurized sea. This is the precise nursery where the first stable droplets of strange matter, those ice-9 seeds of the cosmos, could theoretically be born. While the other experiments at CERN are hunting for new laws of physics, Alice is probing the limits of the laws we already have. They are asking how much pressure the fabric of reality can take before it undergoes a phase transition into something else. The cauldron of Alice is the ultimate testing ground for the stability of our world. We are taking the most stable elements of our reality, the heavy, dependable atoms of lead, and we are intentionally reducing them to their most primitive, volatile state. We are doing this in the hope that by understanding the soup of the Big Bang, we can finally solve the mysteries of how mass is distributed and how the fundamental forces were forged. But as we stir this primordial cauldron at trillions of degrees, we must acknowledge that we are operating in a realm where the standard safety catches of nature have been removed. In the heart of the Alice detector, for a sliver of time too small to be measured by a human heart, the universe returns to its original state of liquid fire. It is a moment of profound beauty and immense power. But it is also a moment where the Strangelet could cross the threshold from a mathematical nightmare into a physical reality. The Alice experiment is the forge where the future of our planet is being balanced against our thirst for the most ancient knowledge. We are playing with the ingredients of the Big Bang, and the cauldron is bubbling with trillions of strange quarks, all looking for a way to stay. We have built a machine to see the beginning of time, but we must be careful that it does not also provide us with a glimpse of the end. The perfect liquid of the Big Bang is back, and it is vibrating with the potential to rewrite the recipe of the world we know. The heat generated in the heart of the Alice experiment is a number that truly defies human comprehension, transcending the limits of standard measurement and entering the realm of cosmic absurdity. We are talking about 5.5 trillion degrees Celsius. To call this hot is a staggering understatement. It is a temperature roughly 100,000 times hotter than the center of the Sunday. At this extreme, the very concept of heat undergoes a transformation. In our everyday lives, heat is the vibration of atoms, but at 5 trillion degrees, atoms have long since been obliterated. Even the protons and neutrons, the heavy, stable hearts of matter, have reached their breaking point and melted away. What remains is a searing, microscopic fireball of the most primordial substance in existence. For a few years, physicists expected this substance to behave like a superheated gas, a chaotic cloud of particles flying in every direction. But when the data from the first heavy ion collisions began to pour in, the universe delivered a shocking revelation. The hottest substance ever created by humanity does not behave like a gas at all. It behaves like a perfect liquid. This perfect liquid is a state of matter so smooth and so low in viscosity that it challenges the absolute mathematical limits of physics. To understand viscosity, think of the difference between pouring honey and pouring water. Honey is thick and resistant to flow. It has high viscosity. Water is much thinner and flows easily. But even water has internal friction molecules rubbing against each other, creating tiny amounts of resistance. The Quark-Gluon Plasma created at CERN is different. It possesses a viscosity so close to the theoretical minimum, a value dictated by the laws of quantum mechanics, that it flows with almost zero internal friction. It is a fluid of such incredible harmony that the individual quarks and gluons move as a single, unified collective. If you were to stir a cup of this liquid, It would theoretically keep swirling forever, never losing its momentum to friction. It is the smoothest, most perfect substance ever observed in the history of science, a shimmering, subatomic ocean that existed only for a heartbeat during the dawn of time. However, the perfection of this liquid is exactly what makes it so potentially dangerous. In our normal, cold world, the up and down quarks are locked away in their separate bags, preventing them from interacting in any way other than the standard laws of chemistry. But inside this boiling, low-viscosity cauldron, the barriers are gone. This is a realm of total subatomic freedom. Because the energy levels are so high, the law of mass-energy equivalence allows the sheer heat of the collision to spontaneously manifest as physical mass. Trillions of degrees of energy are instantly converted into a teeming, chaotic sea of strange quarks. This is the only place on the entire planet where these heavy, exotic, third-flavor quarks are produced in such massive, concentrated quantities. In the fraction of a second that the plasma exists, the ALICE detector is filled with a soup containing roughly equal numbers of up, down, and strange quarks, all swirling together in a dense, pressurized, and perfectly fluid environment. This is the link that transforms a brilliant scientific experiment into a potential existential nightmare. The Quark-Gluon Plasma is the only known nursery where a strangelet could theoretically be born. In the chaos of this perfect liquid, the three flavors of quarks are not just passing each other, they are colliding and combining in trillions of different permutations. Most of these combinations are unstable and vanish instantly as the plasma cools. But if the Strangelet hypothesis is correct, there is a specific, magical ratio, a sweet spot of up, down, and strange quarks that forms a state of absolute stability. Because the plasma is a perfect fluid with no friction, these quarks can find each other and snap into this true ground state with terrifying ease. It is like a cosmic puzzle where the pieces are vibrating so fast that they eventually find the only configuration that locks them together forever. The birth of a strangelet within this plasma would be a quiet, microscopic event, completely invisible to the naked eye, yet it would represent the first seed of the cosmic infection. In the searing heat of the ALICE cauldron, this seed would find itself surrounded by an ocean of free quarks, providing it with an infinite buffet of matter to consume. While the plasma itself only lasts for a fraction of a second before cooling back into normal matter, a stable strangelet wouldn't care about the cooling. It would remain frozen in its state of ultimate stability, a microscopic drop of indestructible liquid sitting at the bottom of the energy hill. The very perfection of the fluid created at CERN is what facilitates this transition. Because there is no resistance, no friction to slow the process down, the transition from normal matter to strange matter could happen with the speed of a quantum snap. We are, in effect, building a microscopic version of a neutron star right here on Earth. The conditions inside the ALICE detector, the crushing pressure, and the trillions of degrees of heat are the only conditions in the universe capable of forcing the third flavor to become a permanent resident. We are stirring a pot that is 100,000 times hotter than the sun, filled with the most contagious ingredients in the cosmos, and we are doing it with the most perfect stirring rod ever devised. The scientific community remains confident that these droplets are too small and too hot to remain stable, that they will evaporate into harmless radiation long before they can do any damage. They argue that the universe has been performing these experiments for billions of years via cosmic rays without destroying the moon or the sunday. But there is a subtle, haunting difference between a random cosmic ray hitting a planet and the controlled, high-density environment of the ALICE experiment. At CERN, We are concentrating the energy. We are maximizing the density. We are creating a sustained, perfect liquid that provides the ideal environment for the strangelet to nucleate and grow. We have created a state of matter so alien to our world that we have to look back to the Big Bang just to find a comparison. The Quark-Gluon Plasma is a masterpiece of modern physics, a triumph that allows us to see the very first moments of our history. But as we marvel at the smoothness of this primordial soup, we must remember that it is also the only place where the recipe for our destruction could be successfully cooked. We have created the hottest, most perfect liquid in the universe, and we have filled it with the ghosts of the strange quarks, waiting to see if they finally decide to stay. To truly understand the terrifying potential of the liquid being brewed at CERN, we must lift our eyes from the microscopic detectors of the ELICE experiment and look toward the most violent and extreme corners of the observable universe. While the strangelet remains a haunting mathematical possibility in our laboratories, the cosmos may have already been conducting this experiment on a gargantuan scale for billions of years. To find the real-world manifestation of this strange liquid, we have to travel to the graveyard of the stars, specifically to the remnants of massive suns that have long since exhausted their nuclear fuel and collapsed under their own weight. This brings us to the most enigmatic and dense objects in the sky: neutron stars. A neutron star is essentially a city-sized atomic nucleus, a sphere of matter so incredibly dense that a single teaspoon of its material would weigh as much as Mount Everest. These are objects where the standard rules of matter are pushed to their absolute breaking point, and it is here, in these celestial pressure cookers, that the strange star connection begins. In the standard model of astrophysics, a neutron star is composed almost entirely of, as the name suggests, neutrons. When a massive star goes supernova, gravity wins the ultimate battle, crushing the star's core with such ferocity that it forces electrons and protons to fuse together into a solid sea of neutrons. For decades, we believed this was the final destination for dead matter. We assumed the internal pressure was balanced by neutron degeneracy pressure, a quantum mechanical wall that prevents these neutrons from collapsing any further. But theoretical physics suggests that, at the very heart of these stars, where the gravity is most intense, the pressure becomes so overwhelming that even the bags containing the quarks, the neutrons themselves, begin to overlap and dissolve. In this high-density inferno, the up and down quarks are set free, creating a localized pocket of Quark-Gluon Plasma, very much like the perfect liquid we are currently creating at CERN. This is where the hypothesis takes a dark and fascinating turn. If the energy levels at the core of a neutron star are high enough, and if the Strangelet hypothesis is correct, the up and down quarks will spontaneously begin to transform into strange quarks to relieve the pressure and find a lower energy state. If strange matter is indeed the true ground state of the universe, the ultimate, most stable form of matter, then this conversion wouldn't just stay localized at the core. Just like the ICE-9 infection we discussed, the moment a small seed of stable, strange matter forms in the center of a neutron star, it would begin to convert the surrounding normal neutrons into more strange matter. The infection would spread outward from the core at a significant fraction of the speed of light, consuming the entire star from the inside out. In a matter of seconds, what was once a normal neutron star would be reborn as a strange star. A strange star is not just a dense object. It is a single, macroscopic entity made of a perfect, indestructible liquid. Because strange matter is more stable and denser than normal neutron matter, a strange star would be slightly smaller and significantly smoother than a traditional neutron star. It would be a sphere of absolute crystalline perfection, possessing no crust and no internal layers, just a solid, shimmering ocean of up, down, and strange quarks bound together in a unified quantum state. This is the cosmic scale of the liquid being brewed at CERN. If these stars exist, then strange matter isn't just a theory or a possibility, it is a celestial fact of life. It would mean that the most stable, long-lived objects in the universe are not made of the atoms we are familiar with, but of this exotic, three-flavored slurry. The properties of a strange star would be unlike anything else in the cosmos. Because strange matter is held together by the strong nuclear force rather than just gravity, a strange star would be practically indestructible. You could theoretically throw a normal planet at a strange star, and it would simply be processed into more strange matter upon contact, adding to the star's mass without disturbing its structural integrity. These stars would be the ultimate survivors of the universe. While normal stars eventually burn out and white dwarfs cool into black cinders, a strange star could potentially exist for trillions upon trillions of years, outlasting the very galaxies that birthed them. They are the indestructible, ultra-dense spheres that represent the final, terminal state of matter in a cooling universe. Some astrophysicists believe we have already seen these monsters. There are certain compact objects in our galaxy that appear to be too small or too dense to be standard neutron stars. They rotate with a terrifying stability and emit radiation in ways that suggest a perfectly smooth, liquid surface. These might be the strange stars that have already crossed the threshold. If this is true, it means the universe is already partially infected. It means the standard recipe of up and down quarks has already been replaced in the most extreme environments by the strange recipe. The cosmos is telling us that our version of reality, the one made of tanks, jets, and humans, is just a temporary fragile skin on the surface of a universe that is slowly, inevitably turning into strange matter. This realization places the experiments at CERN into a much larger, more haunting context. When the Alice experiment smashes lead ions together to create a Quark-Gluon Plasma, it is not just simulating the Big Bang, it is creating a microscopic piece of a strange star right here on our planet. We are essentially forging a mini-star in a subterranean tunnel, testing to see if the rules that govern the centers of dead galaxies also apply to us. The bridge between the microscopic world of the lab and the macroscopic world of the strange star is the stability of that liquid. If we can prove that strange matter exists in the hearts of neutron stars, we prove that the true ground state is real. We confirm that our world is sitting on that high, unstable plateau, waiting for a spark to send it tumbling into the deeper valley. The connection to these cosmic monsters is a reminder that the laws of physics do not care about human comfort or the permanence of our planet. The universe is a vast, cold machine that is constantly seeking the most efficient and stable configuration. If that configuration is a liquid of three flavored quarks, then the universe will eventually find a way to make it. The strange stars are the silent witnesses to this inevitability. They are the grey goo of the cosmos, already drifting through the dark, having already undergone the transformation that we are currently flirting with in our particle accelerators. They represent the ultimate triumph of the strange quark, a particle that we consider exotic and unstable, but which might actually be the primary building block of the final, finished universe. As we contemplate these indestructible, ultra-dense spheres, we are forced to ask if we are the ones who are out of place. We look at a strange star and see a terrifying anomaly, but from the perspective of the cosmos, we might be the anomaly, a temporary, high-energy glitch made of up and down quarks that only exists because the temperature is currently low enough to allow us to survive. The strange star connection shows us that the liquid that can devour Earth is not a new invention. It is an ancient, fundamental reality of the scale of stars. We are just the latest species to discover the recipe, unaware that the kitchen has been open for billions of years and the most stable dish on the menu is us. We are playing with the fire of the stars, and the stars have already shown us what happens when that fire never goes out. It is perfectly natural and arguably a sign of a healthy survival instinct to feel a cold shiver of existential dread when discussing a substance that could theoretically reduce our entire planet to a shimmering, soccer stadium-sized ball of exotic slurry. When we hear words like perfect liquid, primordial soup, and contagious matter, the human mind immediately reaches for the most catastrophic parallels, the Ice Nine of fiction or the unstoppable grey goo of a nanotechnology disaster. We find ourselves staring at the headlines from Geneva and wondering why, if the Strangelet Hypothesis is a legitimate scientific theory, the world hasn't already ended. Why are we still able to wake up, drink our coffee, and worry about the mundane details of our lives, while the most powerful machine in history is purportedly stirring a cauldron of doomsday particles just beneath the surface of the European countryside? The answer lies in a series of rigorous, fundamental, physical safety catches that nature has built into the very fabric of reality, safeguards that ensure the world is much harder to destroy than a Hollywood script might lead you to believe. The first and most significant line of defense against a subatomic infection is something physicists call the Coulomb barrier. To understand this, we have to look past the contagious nature of a strangelet and focus on its physical personality. Every atom in your body, in your car, and in the Earth's crust is protected by a fortress of electrical repulsion. At the center of every atom is a nucleus packed with protons, which carry a positive electrical charge. According to the prevailing theories of strange matter, a small, newly formed strangelet would also carry a significant positive electrical charge. As any school child with a pair of magnets can tell you, like charges violently repel each other, for a strangelet to infect an atom, it must physically touch the nucleus to begin the conversion process. However, as a positively charged strangelet approaches a positively charged nucleus, the electromagnetic force pushes back with a ferocity that increases the closer they get. It is a form of subatomic social distancing enforced by the fundamental laws of the universe. In the low-pressure, low-density environment of a laboratory or the Earth's surface, a strangelet simply cannot get close enough to a normal atom to eat it. It would be like trying to push the north poles of two incredibly powerful magnets together. No matter how hard you push, they will veer away from each other. In the heart of a neutron star, the crushing weight of an entire sun provides the brute force necessary to overcome this barrier. But on Earth, that pressure simply doesn't exist. Without that external force to jam the particles together, the strangelet and the atom are destined to remain apart, separated by an invisible, impenetrable wall of electrical hate. The second major safeguard is a matter of thermodynamics and the sheer, blistering violence of the CERN collisions themselves. As we have explored, the Quark-Gluon Plasma created in the ALICE experiment is trillions of degrees hot, literally the hottest substance ever recorded. While this heat is necessary to melt the bags of protons and neutrons and set the quarks free, it is also the very thing that prevents a stable strangelet from forming and surviving. Think of it like trying to build a snowball in the middle of a blast furnace. Even if you have all the right ingredients, the up, down, and strange quarks, the sheer thermal energy of the environment makes it impossible for them to stick together in a stable, cooling drop. For a strangelet to become a seed of destruction, it doesn't just need to be created. It needs to be cold enough to hold its shape and begin bonding with other matter. But at CERN, the perfect liquid exists for only a fleeting microsecond before it expands and cools so rapidly that it essentially evaporates. By the time the environment is cool enough for a strangelet to be stable, the density of the quarks has dropped so low that they can no longer find each other to form a cohesive drop. The cauldron at CERN is simply too turbulent and too short-lived to act as a nursery for a permanent, world-eating monster. The laws of entropy dictate that the energy will dissipate far faster than the infection can take root. However, the most powerful and comforting safety certificate for the Large Hadron Collider doesn't come from a laboratory report or a computer simulation. It comes from the moon, the sun, and the billions of years of history written in the stars. This is known as the cosmic ray argument. Humanity may be new to the game of smashing particles together at nearly the speed of light, but the universe has been doing it since the beginning of time. Our galaxy is a shooting gallery of high-energy particles called cosmic rays, protons, and nuclei, screaming through the void at velocities that make the LHC look like a slow-motion toy. For over 4 billion years, these cosmic rays have been slamming into the surface of the moon with energies far exceeding anything we can achieve at CERN. The moon has no atmosphere to act as a shield. It is a giant silver particle detector that has been subjected to a relentless, high-energy bombardment for eons. If high-energy collisions were capable of creating stable, world-eating strangelets, the moon would have been converted into a dense ball of strange matter billions of years ago. It would be a strange moon by now. The same logic applies to the sun, the planets, and every other solid object in the sky. The fact that the moon is still a boring grey rock made of normal silicate and the sun is still a glowing ball of normal plasma is the ultimate proof that nature's safety catches are working. The experiment has already been run trillions of times by the cosmos, and the result is always the same. We are still here. We must also address the common fear that by concentrating the collisions in a specific spot, CERN is doing something different or more dangerous than nature. But even this doesn't hold up to mathematical scrutiny. The density of collisions at the LHC is still millions of times lower than the density of impacts occurring naturally on the surface of white dwarf stars or in the atmospheres of dense planets across the galaxy. If there were a tipping point, where matter becomes strange, the universe would have tripped over it a long time ago. We are not playing with fire in a room full of gunpowder. We are trying to strike a tiny match in the middle of a vast, damp forest where the trees refuse to catch. This brings us to the core of scientific candor. While the Strangelet Hypothesis is a fascinating area of theoretical study, the consensus among the global physics community is that the risk of a global catastrophe is effectively zero. It is not just unlikely, it is forbidden by the very laws of electromagnetism and thermodynamics that allow the world to exist in the first place. The scientists at CERN are not reckless gamblers. They are meticulous observers who have subjected their experiments to years of safety reviews and independent audits by the world's most skeptical minds. They aren't dead because they know exactly where the boundaries of reality are. So, why do we still talk about it? Why does the strange matter doomsday scenario continue to captivate our imagination? Because it reminds us that our normal world is a fragile, beautiful exception to the rule. It reminds us that we live in a narrow window of temperature and pressure that allows up and down quarks to be the kings of the hill. The safety check isn't just a list of reasons why we won't die today. It's an appreciation of the incredible, fine-tuned balance that keeps the universe normal for us. We are protected by the Coulomb barrier, shielded by the fleeting nature of high-energy fireballs, and vindicated by the ancient, silent testimony of the moon. We are playing with the ingredients of the stars, but the stars themselves have already given us their permission. We can peer into the perfect liquid of the Big Bang with curiosity rather than terror, knowing that the Ice Nine of the cosmos is a ghost that cannot cross the threshold of our reality. If we can move past the instinctive existential terror of a subatomic infection and look toward the cold, calculated potential of engineering, we find ourselves standing at the gateway to a technological singularity. To transition from fearing the strangelet to harnessing it is to move from being a victim of the universe's laws to being their architect. The primary challenge, of course, is the absolute necessity of stabilization. Currently, the perfect liquid created at CERN exists for a duration so short it is measured in yoctoseconds, vanishing the moment the intense heat and pressure of the collision dissipate. But theoretical physics suggests that if we could find a way to bottle this liquid, perhaps through advanced superconducting magnetic traps, or by discovering a quantum freezing method that keeps the three flavors of quarks in their liquid state at lower temperatures, we would possess the single most transformative material in the history of the human race. We would be stepping out of the standard era and into the era of infinite density, the ultimate aegis, strange armor, the most immediate and jaw-dropping application of stabilized strange matter lies in the realm of advanced defense and heavy industry. In our current world, the protection of a main battle tank or a high-altitude interceptor is a constant trade-off between weight and durability. To stop a modern kinetic energy penetrator, you need decimeters of high-grade depleted uranium or complex ceramic composites, adding tens of tons to the vehicle's weight and limiting its mobility. But strange matter changes the geometry of survival. Because strange matter is hundreds of trillions of times denser than lead, its structural integrity is not maintained by chemical bonds between atoms, but by the strong nuclear force itself, the most powerful force in nature. Imagine an armor plating for a next-generation combat vehicle that is only 1 inch thick, yet possesses the defensive threshold of a 10-mile-thick mountain range. At this level of density, the concept of penetration becomes physically meaningless. A standard anti-tank missile or a high-velocity railgun slug striking a plate of strange armor would not dent, crack, or pierce the material. Instead, the projectile would experience a collision so violent and absolute that its own atomic structure would be instantly atomized. The kinetic energy would be absorbed and dissipated across the liquid lattice of the quarks, with almost zero deformation of the armor itself. This would allow for the construction of invincible platforms, tanks that weigh no more than a family car, but can shrug off a direct hit from a tactical nuclear weapon, or fighter jets that can fly through a storm of flak without a single scratch on their airframes. We are talking about a world where the sword no longer has any hope of defeating the shield. The supernova in your pocket, infinite energy storage. Beyond the physical protection of the armor, the mastery of the perfect liquid offers the ultimate solution to the human race's eternal struggle for energy. Current battery technology is embarrassingly primitive. We rely on the slow, clunky movement of lithium ions to store a tiny fraction of the energy required to run our digital lives. Even nuclear fission and the theoretical promise of fusion are messy, high-volume affairs. However, because strange matter exists at the true ground state, the absolute bottom of the energy hill, it represents the most efficient energy battery possible in the cosmos. Theoretical models suggest that we could create strangelet batteries that pack the cumulative power output of a supernova into a device the size of a common coin. Because the energy density of the Quark-Gluon Plasma is so high, a few micrograms of stabilized strange liquid could provide enough electricity to power a sprawling metropolis for a century, or keep a massive deep space carrier operational for its entire multi-generational journey. This isn't just clean energy, it is limitless energy. The scarcity that has driven every war and geopolitical conflict in human history would evaporate overnight. A single Strangelet battery could replace an entire fleet of oil tankers or a dozen coal-fired power plants. On the battlefield, this allows for the deployment of directed energy weapons, lasers, and particle beams with a sustained power output that could vaporize entire carrier groups from across the horizon, fueled by a power source that never needs to be recharged. The aerospace revolution, crossing the interstellar void. While the military and industrial applications are staggering, the true destiny of strange matter lies in the aerospace revolution. We are currently a species shackled to our planet by the tyranny of the rocket equation, forced to carry massive tanks of chemical fuel just to move a tiny capsule. Strange matter provides the exit ramp from this limitation. A spacecraft utilizing a strange matter catalyzed engine would not need to carry fuel in the traditional sense. By utilizing the matter-to-energy conversion properties of the Strangelet, such a ship could use any form of ballast, even space dust or asteroid debris, and convert it into pure, high-energy thrust with nearly 100% efficiency. This represents the end of the chemical rocket era and the beginning of the interstellar era. A ship powered by the perfect liquid could maintain a constant acceleration of 1g, providing its crew with comfortable artificial gravity while simultaneously reaching a significant fraction of the speed of light in a matter of months. We would no longer be talking about trips to Mars. We would be talking about commutes that take hours. The outer gas giants would be days away. The nearest star systems, currently thousands of years beyond our reach, would become accessible within a single human lifetime. Strange matter is the material that turns the universe from a vast, empty barrier into a navigable highway. It allows us to build ships that are essentially microscopic stars, carrying the concentrated power of the Big Bang within their hulls to illuminate the dark path to other worlds. The strategic singularity and the New World Order. The nation or entity that first achieves the stabilization of strange matter will instantly become the undisputed master of the planet. We are looking at a strategic singularity where all conventional military technology becomes obsolete in an afternoon. A stealth drone protected by strange matter skin and powered by a coin-sized quark battery could stay airborne for decades, possessed of an sensor suite with infinite range and weapons that never run out of ammunition. It would render traditional radar, missile defenses, and even nuclear deterrence completely irrelevant. The world would shift from a balance of power to a total hegemony of whoever holds the strange recipe. However, the tech reality of strange matter also demands a new kind of responsibility. To wield a material that is as dense as a mountain and as energetic as a star is, to hold the life and death of the planet in a single container. If the stabilization fails, or if the infection is accidentally triggered during a manufacturing process, the strange armor doesn't just protect the tank, it begins to consume the world. This is the ultimate double-edged sword, a material that offers us the stars, but only if we are perfect in our control of it. There is no room for error when you are engineering with the true ground state. Every factory becomes a potential ground zero for a planetary collapse. We would be a civilization that has finally achieved the power of gods, but we would be forced to live with the constant, shivering awareness that our indestructible future is built upon the most dangerous substance in existence. As we look at the vibrating, shimmering liquid deep within the Alice experiment, we are looking at the raw clay of a new age. We are seeing the end of scarcity, the end of vulnerability, and the end of our planetary isolation. Strange matter is the forbidden fruit of the military-industrial complex, a substance so powerful it could turn the Earth into a paradise or a silent, dense ball of grey goo. We are learning to cook with the ingredients of the stars, hoping that we can find a way to serve the future without burning the kitchen down. The liquid is there, the density is real, and the potential is infinite. All that remains is for us to see if we are brave enough or foolish enough to take it out of the cauldron and build a world out of it. As we emerge from the subterranean depths of the Alice detector and leave behind the searing 5 trillion degree fire of the Large Hadron Collider, we are forced to confront a reality that is as haunting as it is magnificent. We have spent tonight journeying through the most extreme kitchen in the cosmos, watching as humanity learns to cook with the very ingredients that forged the Big Bang. This pursuit of the Strangelet is not merely another chapter in the long history of particle physics. It is the ultimate test of our species' maturity. In our hands, we hold the potential for 2 diametrically opposed futures. We are staring at a substance that is either the most dangerous Ice-9 contagion in existence, a liquid that could accidentally reduce our vibrant blue home to a silent, dense ball of grey goo, or it is the ultimate building block of a future we can barely imagine. It is the forbidden fruit of the subatomic pantry, and once we have tasted the knowledge of how to create it, there is no returning to the blissful, ignorant stability of the world we knew before. The story of strange matter is, at its core, a story about the staggering fragility of what we consider normal. We have spent thousands of years building civilizations, composing symphonies, and engineering miracles, all based on the assumption that the standard recipe of up and down quarks is the final, finished version of reality. We looked at the heavy, unstable, strange quark as a fleeting ghost, a subatomic pariah that had no place in our cold, quiet world. But the experiments at CERN and the silent testimony of the neutron stars in the deep void suggest that we are the ones who are out of place. We are the anomaly. Our normal world of tanks, jets, and human hearts exists only by a slim, precarious margin of error. We are living on a high-energy plateau, protected from the true ground state of the universe only by the fact that the fire of the Big Bang has cooled. We are a temporary glitch in a universe that, given the right pressure and the right spark, would much rather be a perfect, indestructible liquid of three-flavored quarks. This realization is the ultimate humbling of human arrogance. It tells us that our existence is not guaranteed by the laws of physics, but merely permitted by them for a short duration. We have spent our history assuming that being normal was an absolute shield, a cosmic safety catch that prevented the universe from dissolving into exotic slurry. But as we push the Large Hadron Collider to its absolute limits, we are realizing that we are the ones removing that safety catch. We are the ones providing the heat, the density, and the environment where the ghosts of the strange quarks can stop decaying and start existing. We are inviting the third flavor into our home, unaware that it has the power to burn the house down just by standing still. Strange matter is the ultimate predator of the subatomic realm, a substance that doesn't need to attack us to destroy us. It only needs to touch us. Yet, we cannot ignore the siren call of the potential it offers. To turn away from the Strangelet because of fear would be to turn away from the stars themselves. If we can master this liquid, if we can learn to stabilize it and harness its infinite density, we will have finally achieved the power of the architects of the cosmos. We are talking about armor that makes war obsolete because no weapon can pierce it. We are talking about energy storage that packs the power of a supernova into a device you can hold in your hand, ending scarcity and poverty in a single generation. Most importantly, we are talking about the key to interstellar travel. Strange matter is the fuel of the true starship, the material that will finally allow us to cross the light years and claim our place among the galaxies. It is the master key to a Type 1 or Type 2 civilization, a prize so great that it makes the risk of a grey goo doomsday feel like a necessary gamble. This is the central paradox of human progress. The more we understand the universe, the more dangerous our relationship with it becomes. We have moved from fire to steam, from electricity to the atom, and now we are reaching for the very fabric of space-time and the primordial soup of creation. Every time we have unlocked a new level of energy, we have faced the possibility of our own destruction. Strange matter is simply the final boss in this long game of technological evolution. It is a material that demands perfection. There is no room for a leak in a strange matter factory. There is no room for error in the magnetic traps of the ELICE experiment. We are becoming gods, but we are doing so while still carrying the flaws and the impulses of the primates we evolved from. We are cooking with the ingredients of the Big Bang, hoping that we can serve the future without burning the kitchen down. The universe is normal only by a sliver of probability, a temporary state of equilibrium that we are currently vibrating with the most powerful machine ever built. We are peering into the perfect liquid of our birth and seeing the potential for our end. The Strangelet is a reminder that the universe is under no obligation to remain comfortable for our convenience. It is a cold, mathematical landscape of valleys and peaks, and we are currently poking at the ground to see how deep the next valley goes. Whether we find a new world of infinite potential or a silent, dense ball of exotic slurry depends entirely on our ability to control the strange ghosts we are summoning. We have reached for the forbidden fruit, and the taste is one of absolute power and absolute danger. Before we conclude this investigation into the liquid that can devour the earth, I want to leave you with a question that touches the very heart of this scientific dilemma. We are at a point where our knowledge is outpacing our wisdom, and the Strangelet Hypothesis forces us to make a choice. If you were a lead scientist at CERN, and you had the choice to create a new material that was absolutely indestructible and offered infinite clean energy, but it carried a 1 in a million chance of accidentally triggering a chain reaction that would destroy the entire world, would you still make it? Is the potential of the stars worth the risk of the grey goo? Let me know your thoughts in the comments below. I want to know if you think the reward of absolute knowledge justifies the risk of absolute destruction. We are standing on the edge of a new reality, watching the cauldron of the Alice experiment bubble with the heat of the Big Bang. The third flavor is waiting, the true ground state is calling, and the future of our planet is being balanced in a subterranean tunnel in Geneva. It has been a pleasure exploring the darkest and most strange corners of physics with you tonight. We have much more to uncover in the coming weeks as Run 3 continues to push the boundaries of what is possible. If you want to keep exploring these cosmic mysteries with us, let me know which impossible particle we should hunt for next. Thank you for being part of the lab tonight. Good night, and see you in the next video.